Good morning.
Good morning. Oh, that is video. That is double. That's awesome. I didn't even know. That's awesome. That is.
Good morning, Professor.
Good morning. Good morning, folks. I'm saying good morning to everybody. I'm particularly saying good morning to our special guest. And I'm stupidly trying to adjust my screen so I see the guest better. That's so dumb. Hello, hello. That's awesome. How old are we? Oh, I guess your mute is on. I guess that's a good idea.
He's one.
That's the best. That is the best. All right. Someone's going to be someone in this room is going to get hyper educated today, or at least for a couple of minutes. That's great. And that definitely counts as an interview. Okay, I'm not going to overdo this. I totally appreciate it. I totally get it. I'm going to say hello to and that is guts on many levels, no question. Okay, good morning. Yes, I'm going to say good morning to everybody now. Sorry. All right, I'm getting swept away. There's nothing better than children that are not my own, who are not in my room bothering me. Okay. No, I love my own. Oh, wait, more people are coming in. Hold on. Okay. No, that's totally awesome. And I understand if it gets too difficult in any direction. Okay. Good morning. Wait, let me look in the chat. Good morning, David. Good morning to me. I mean, hi, Tamika. Good afternoon, Noelia. Good afternoon, Liani. Good morning, Ariella. Good afternoon, Zitlali. Good afternoon, Asia. Got your message. Good afternoon, Juanita. Good afternoon, Jean-Pierre. Good afternoon, Jenna Marie. Good afternoon, Shakia. Good afternoon, Jacob. Good afternoon, Edie. Good morning, Yasmin. Good morning, Michelle. Good afternoon, Janine. And wait, there's more. And obviously, good afternoon, Catherine and guest, or a one-year-old guest, which is awesome. Let's see. Who else did I miss? Oh, and good afternoon, Hoyin, whose name I might still not be saying right. Oh, good afternoon, Renice. Oh, I'm glad you're here, Renice. That's great. I get it. You're in the right place. I won't embarrass anybody. Well, I mean, I won't on purpose. Anyway, good to see you, Renice. You're in the right place. Who else? Wait a minute. I think. Good afternoon, Shakia and Janine. Oh, here comes Antonio. Okay. I think that's awesome. That's awesome. Yes, no, totally. Oh, that's great. And thank you for using the chat, Renice. And I hope I'm saying your name right. And yes, finally. And I know it took a while. Totally appreciate how patient you were about all that stuff. We will catch you up. Don't I'll say that and I don't want to like single you out or whatever too much, or at least not at the moment. The main thing, Renice, and anybody, and there are other people. Okay, so still. Even though I know the course flies and we're already in week 2 of a 5-week deal and all that, but there are still people joining. I mean, and yes, let's say hello to Renice, but she's not the only one, and it's totally not her fault, and it's not a question of fault. But anybody who is joining this week or joined in the last couple of days, the main thing, the most important in terms of like catching up or getting caught up or whatever, the main thing to everybody is please do join the Google Classroom. Oh, and hello, Antonio. Good morning. Good afternoon. The main thing, like we don't do anything, and I know for some of you have heard this a million times, but we don't do anything really through Blackboard. We do everything, and I mean everything, through Google Classroom. So anybody who's not, and I'll try to right now, actually, I think I could put the link right in the chat. But if there's any question in your mind at all, whether you've joined the Google Classroom, please make sure to do so. Let me put the chat in the, let me put the link in the chat right now, if I can, which I think I can. Wait, I'm looking at 2 things at once. No, maybe I can. Or maybe somebody else has it. Wait, hang on. This is just, all right, I'm going to take one more second to try to do this from here, because it is, everything happens in Google. Oh, that's awkward. Hold on. I didn't mean to do it publicly. All right, hold on. Bear with me for a second. I know just about everybody has, and I know that, and that's great. And I've been getting the homework from people and all of that, but just in, yes, okay. I think this is it. Right. If there's any question in your mind about whether you have joined the Google Classroom class, the link is in the chat now. Again, if you have used Google Classroom before for any other class in your life, good, then I think you'll find this straightforward. If you haven't, it's still fairly straightforward. I mean, it's like Google. But the first thing is just please use that link that I just put in the chat. If you have not, you can use email address you want. It doesn't have to be John Jay. It doesn't have to be. Oh, actually, all right, I'm going to pause a second, repeat this because it's actually somewhat in particular for the person who's just joining again. Okay. Okay. I'm just going to say this again. So please, everybody who has not, oh yeah, no problem. No worries. And thank you. Thank you for being so communicative. You'll see soon that I really appreciate that it like counts in this class, that you're being so communicative and so much a part of it. I'm telling everybody, I think maybe it doesn't even apply to you. You might have already done it. And I'm sorry if I haven't. Actually, I could check right now. No, I keep doing this publicly. I don't. Well, if you haven't joined the Google Classroom, please use that link that's right there in the chat. It's sort of self-explanatory once you get there, even if you haven't, sort of. You can use any email address you want, as long as it's an email. Yeah, I think maybe you haven't yet. Oh, no, wrong class. You can use any email address you want. I don't really mean to be doing this on my screen right now, but I am. Oh, no, you did already. She totally did. She's a total, okay. I am a loser. She is awesome. Okay, so I think everybody probably is in the Google Classroom. That is great. And I appreciate it. All right, to everybody, we're gonna get rolling in a second. I sort of had suggested, oh, yeah. All right, wait, direct chat. Let me do. Oh, yes. Okay. There's a question in the direct chat, which is a very fair question, and I will answer it. Let me back up for a second. All right, we're going to get rolling in a moment. Getting rolling means going back to going over the homework that we're in the middle of, which specifically right now means the very last question of homework 1. So yes, let me repeat to everybody, we are still on homework sheet 1. And I know that's funny. Maybe it's even unusual. It's not unusual for this class. We always take a long time to go over homework 1 because so much is based on it. We will get faster and faster every day, including today. Hopefully we will get faster and faster. Hopefully we will get faster and faster. That means both with like my pace of going over things, and it means with like what I expect you guys to be turning in. But I will never expect you to be substantially ahead of where I am. I will always expect you to be about one homework assignment ahead of where I am. Like I will expect you to try the homework before I'm going over it. With more people coming. But that's about it. But I have to just keep putting the homeworks in the pile, and I have to keep pacing myself to get faster and catch up with them. So there's a good question in the direct chat about homework points. I will address it in a moment, but let me just reiterate to everybody before we get rolling. I'm going to be today continuing to go over question number 9 in homework 1. Most of you have tried this and gotten it back. A few of you just turned it in like last night or something, and I haven't turned it back to you yet. That's my bad. I see that you did it like fairly like over the weekend. I haven't turned it back yet. More people coming. Let me just say again, if you didn't get full credit on the homework I think is worth 250 points or something. If you didn't get full credit, if you lost a lot of points, you totally can redo it to get the extra points back. It's not a problem. If you didn't lose a lot of points, I wouldn't worry about it. Like if you got like a 225 or a 230 out of 250, I would just let it go and move on with your life. But again, both with me and with you guys, deadlines are more like all the deadlines in Google Classroom are there for sequencing purposes. It's all to let you know what's coming next and what goes before what or after what. Technically, homework 3 has now been posted, and technically it's due this Wednesday. But really what's due is whatever you're next up to. If you've already done homework 1, and you're waiting to get it back, go on to homework 2. We may or may not get to it today. Honestly, I mean, I think we should actually, but it does, like, you're just always, and I know I've said this to some people before, but you're always just doing the next thing. If once you get that thing back, if you didn't do that well on it and you want to do it again, you totally can. There's no penalties for lateness. There's no penalties for second draft. It's nothing like that. It's just a pile of work that we're all just trying to do in a sequence as best we can. Like, honestly, to everybody, okay? And I've already fallen behind this weekend. That is to say, a lot of you, about half of you have turned in homework too. I have not given it back to you yet. That's my bad. And so if you only turn in half of it, you want to turn in more tonight, great. And again, I see who you are. I know you've done the work, but I haven't gotten it back to you yet. I haven't gotten, if I start going over it today and that helps you do it better, then put the better version in. It's just always about doing the next right thing, if that makes sense, okay? There's no penalties for lateness. There's no penalties for redos or something like that. So now there is a question in the chat I want to answer. And oh, no problem. Thank you, Shamari, for saying that, but no problem. But hello, good to see you. Oh, and good afternoon, Caleb. Thank you for saying that. And oh, and thank you. Wait, oh, Jalali, yeah, did I mess that up? Oh God, yes. Thank you, good point. Let me see if I can fix that quick. There's still a question in the direct chat, which I want to answer. And I'm going to read it out loud, but I'm not going to say the person's name because it is in direct chat. But thank you, Jalali. Wait, let me fix that before I, yeah. So the thing that, what Jalali is getting, there's, all right, now there's 2 questions in the direct chat. Hang on, let me get to them in a second. I'm getting myself, hang on a second. Hang on. What there should be right now though, right. There should be 3 homeworks in your stream, like homework 1, homework 2, homework 3. Technically, and we're still going over the end of homework 1. If you turn in everything on time, you know what? I was going to give a long, vague response about how you're going to find that you're getting tons of points for doing that no matter what. And you are, like, if you're staying on top of everything and turning everything on time, you're doing yourself such a good service. It will come out in that many more points. It'll also give you that many more opportunities to redo things and get more points on better scores. And you'll do better on exams. But you know what? But I can even be more direct. I mean, someone said in the direct chat, do we get, I guess I'm going out of order, do we get extra credit for doing everything on time? I will put in a portal, like a game turn portal that says, like, if you take a screenshot and show that you've turned in everything on time or whatever, and I will give extra points for that. Sure. Like, why not? I mean, I might forget, you can remind me, but sure. And that's the right attitude. Okay, I'm going out of order again. Like, turning things in on time is better than not. And me getting stuff back to you guys fast is better than not. And I think we all know that. And it produces benefits that are multiple. And it also keeps you, the more on time you are, the more, like, the less frantic and the less, like, you ever have to do on a given night, the less you fall behind. And you've all learned all these habits, like, in your career as scientists. And hopefully I have, but not always. So I think, but I am happy to put a portal in to give you even extra credit recognition for that, or to at least to prove to you guys that I notice who's doing that. But at the same time, I want to say to everybody, what I've learned the hard way is, even though there are so many ample, obvious rewards for doing things on time and doing them in sequence and staying on top of things, like, it just makes life so much easier and better. I don't want anybody ever to be extra punished for not doing that, especially in a 5-week course. It's just too difficult. I think there's enough automatic, like, consequences in life for falling behind. It's just stressful to fall behind, and you can't, like, manage as well. But what I never want to send as a message in this class is that it's like that once you're late with something, it's too late. I hate that feeling for me. If you're late with something, you could still totally do it, really. And you could do it for every bit of credit that is there to be gotten. That's the message. So yes, you can get extra credit for being on time, but I don't want anybody to be punished or give up, God forbid, for falling behind. That's, like, the main message I'm sending now. There's another thing in the direct chat I want to address before we go on, but also Jitlali just put in the chat, or the direct chat, she just pointed out that the most recent homework that I posted in, I numbered incorrectly. So thank you. In other words, there should be 3 regular homeworks that you're doing in just in the order that you do them. And we're, 3 real physics homeworks that are worth a lot of points. The first of which we're going to continue going over in a moment. But then there's also the game turn homeworks. For anybody who just recently joined, the bottom line with any homework entitled a game is that any homework entitled a game means it's a moment of self-reflection on ways in which you might have participated in the Zoom class today. Every single day you have an opportunity. I'm just repeating this for anybody who joined late. Like tonight at 11:59 p.m. is due a game turn 4. And Jalali just pointed out that it had said turn 3 a second ago, but that was my mistake. It should have been turn 4. It just take 2 minutes to document, to pull out like a new Word document or a new Google Docs or make a PDF or something and just write like, I asked the question about derivatives today in class, or I said hello today in class, which counts, or I apologize for being late or whatever, or I answered the question about derivatives today. Just jot down in one moment some reminder about how you participated today, and then you submit that and you automatically get 50 points for submitting that. If you never do it, you never get punished, but every time you do it, you get points. And then you'll all see that there's also other game turn, instead of just like turn 1, turn 2, turn 3, turn 4, which is like every day, there's others that have been placed in the chat, and those are due at the end of the semester. You can do them at any time if applicable. Like 1, you get 75 points if you even showed video at all, even for 2 minutes during class, or quirk willing you showed a video of you and your kid or some guest or something. Like you just take the 2 minutes, take out that thing and be like, and maybe show a screenshot, that would help. But I showed video today when I was asking questions about harmonic oscillation, and that's 75 points. Or there's another one that I put in that says worth 1,000 words. I think that one is, if you submit an image or a screenshot or something, some like notes of something that you're doing, or a diagram, if you submitted that to chat and was willing to have us all look at it while we were talking. If you shared a screen, that's worth like 75 points or 100 points or something. So any random ones like that, you just do whenever they're applicable, if applicable, and you just submit them by the end of the semester. But the turns are one for every day. And even saying hello, like even in the chat, does count as participation. All right. Okay. And I know all that is.
Wait, Professor, with all these games, what's the maximum amount of points we can get at the end of the semester?
Well, like, the maximum you can get is tons. I mean, there'll probably end up being like 15 turns. So that's 15 times 50, 75, like 750. Probably the maximum you can get is like 1,000. I mean, it changes every semester. It's something up to 1,000. But
which is how many points to our final grade?
Oh, okay. So that's the thing for me to explain to everybody, maybe a little bit more slowly. The maximum I've ever seen anybody get, literally on their average, the maximum of that plus regular homework, the maximum I've seen anybody add to their average is like 16 points. Let me explain this part slowly, because that's a very fair question. And also, I know there's still a question in the private chat that I still haven't answered. I haven't forgotten, I will. But okay, the maximum so for everybody, all of these points, whether it's the game points that are usually worth like 50 or 75 or 100, or the regular homework points, which are scaled up, right? Like homework 1 was worth like 250. I think homework 2 is bigger. So I think it was worth like 300 or 350. I don't remember. Homework 3 is again small. So it's like 250. All of those points, and I'm just saying this again to everybody. I apologize to anybody who's getting bored hearing this, but like it is important and it is a little bit unusual. Anytime you do a homework for me of any kind and you get, and you get it back and you got those points, that's going into a pile of points for you. Either kind, both kinds of homeworks are all going into one big pile. Let me also say that, say you do homework 1 and you like didn't do it the way I asked, and this goes into the private chat question that I want to answer, but say homework 1 was worth 250 and like you didn't really understand what I was asking, or you never did it my way before. got 150 points on or something, but then but I wrote at the bottom, like, for full 250, please do blah, blah, blah. Or even if I didn't write that on the bottom, if you only got 150 points on a 250 point homework thing, but then you resubmit it at any time you feel like it, I will get notification that you resubmitted. I would appreciate if you also leave your old one there, just so I can see, or I can remember that you did, something, that you were on time with the original one or whatever. But if you resubmit and you now have a better document, and you especially make it clear, like, this is homework version number B or something like that, I will grade that. I will happily give you the full points if that's what it merits. Like, I won't just give you some of them back. As long as we're talking about homework, I'll give them all back. And then your score will be the full score on that. And it will be like the other score never happened, if you know what I'm saying. I mean, like, you will have had to do that much work to get to that point. You will have had to do the homework twice to get all the points, which in my mind means you've totally practiced and you've spent that much time on physics. So yay. But you'll get all the points. So again, partial, just to remind everybody, there's like no time limit on getting these points. There's just time sequences that are advised. But so now now to answer the question, I think it was Jacob's question, I'm not sure. But now by the end of the semester, you have all these points built up, like hopefully all of you, right? And a lot of these points that are built up were from just this easy self-reflection, class participation game thing. You have this big pile of points, and it could be like close to 1,000 points. What I then do is I divide all of your points by a scaling factor. Like, obviously I can't add 1,000 points to your exam average, but I divide the 1,000 by one number, which I cannot tell you right now. I don't know what the number is. It's different every semester, but it is the same number for all students. Like, we come up with it at the end of the semester, and we come up with a number. To be frank, we come up with a number that absolutely makes sure that people get A's. I mean, it's like a curving kind of thing. Believe me, it's not chosen obnoxiously. It's chosen compassionately. But so we come up with a scaling number, and we divide all your points by that scaling number. So say you've built up 1,000 points, and say the scaling number this semester is 100, right? I mean, just arbitrarily. So we would divide your 1,000 points by the number 100. 1,000 divided by 100 is 10. 10 would then be the number of extra points that we would add on, straight up add on to your exam average in order to create your final grade. And to fully answer this question, then the average number of points, like the typical number of points that people do get at the end of the semester for doing all this homework and stuff, typically people do get like 8, 9 points. Often 12 points. Like, the most I've seen is 16. I think that's the most I remember someone getting was 16 points. But people can easily get 12 points average, very easily can get 8 or 9. And then if someone who never ever does any homework, who like never participates, never does anything, they get like 0 added to and their exam average still stands. They don't get punished. They just get nothing added to their.
Sorry, the points get added to your exam average, or they get added to your final grade?
Well, no, I mean, the way it kind of comes to the same thing. The way we make your final grade, and again, this is in the syllabus. This is super important. I mean, obviously you need to know this, so it's worth explaining. So I'm happy you're asking. But if it ever gets confusing, you can find in the syllabus. But the way we make your final grade is we make an exam average first, and your exam average literally consists of this. I'm calling it your exam average. You could call it a raw average or whatever. Your exam average is literally is 3 things: is your midterm, your final, like the midterm in this lecture component of the class, which of course is going to come sooner than we like, but whatever, your midterm, your final exam, and your final average for lab. Like, for everything that you end up doing for Professor Wu in lab, that all together ends up counting like one big exam. In other words, ends up counting as 1/3 of what you did for the whole course. So you have 3 numbers averaged together: one midterm exam, one final exam, and one Professor Wu number. Those gets averaged together. So that's like what I'm calling your exam average, or you could call it your raw average or whatever. That, we have that number. Then to that, we add all these scaled homework points, We add that to that. And then we still also then have reserve the right to give 1 extra point for class participation, like literally 1. And that's because of history. That's like an old tradition that came before all of these systems, and we still just never threw it away. Excuse me. And to be honest, but anyway, so we could still add 1 point then, but then that's your final average, and that's the grade you get in the class. So it's your exam average plus whatever points you got on all these homeworks and all that. So you could have like, you could get an 87, 87, 87, on the 2 exams, 87, 87, and you get an 87 in lab. So you have like an 87 in the class, but then typically like 8 points or something would be added to that because of all your homeworks. So now you have a 95, so you get an A in the class. Does it? And honestly, as long as we're talking about this, does that make sense? And actually, I'm like staring off in space while I'm saying, so I'm not even actually sure who was just asking that, but did I? Oh, wait. Oh, okay. There's a lot.
Yeah, all good. Thanks.
Oh, yeah. Okay. Thank you. All right. Wait. So now there's a lot in the chat. Wait. When I plan to give exams, okay. Yeah, the first, right. Thank you. Yeah. The first exam being the 3rd week, which I know is next week. So soon we got to start talking about it, but I don't want to talk about it today because I want to, roll more with the material. And it'll probably be at the end of next week. It'll probably be Wednesday. Also, it's going to be take home anyway. We'll talk about that as we get a little closer. And there will be a practice exam for it. Like there won't be any surprises by the time we get to that exam. I don't want to get too bogged down in it because as you can see, I can get bogged down somewhat easily. But that's just to answer that in the chat. And yeah, the homeworks. A homework one was worth 200. I was using I'm sorry. If I was saying 250. Oh, yeah. Right. I was saying 250, but then I scaled back homework to 200. Right. That's right. So the different homeworks are.
Wait, so does that mean we lost out on some points, like at the end? How's that going to work?
Well, that's a fair question. I mean, it doesn't mean you lost. Yeah, opportunity cost wise, I suppose. Yes, it means that the total big pile that you could have had at the end is now slightly smaller than it could have been. But don't worry. Yes, it does mean that. But wait, but don't worry about that for 2 reasons. One, the main reason not to worry about that is all these point values and stuff change every semester. Like I make these adjustments all the time. In fact, it used to be that all the homeworks were all worth 50. And then we started realizing we better make the longer homeworks worth more points because that's more fair to everybody to get a lot more points if they're longer. But that's why we don't come up with the scaling factor until the end. Like we're just giving you points as you go in a way that we think is the most like honorable to you. We're just giving you these points. And then at the end, we come up with a scaling factor. And the way that we come up with the scaling factor is I look at all the grades as they're progressing at that point. And I come up with a scaling factor that makes absolutely sure that no matter how badly some people might have done on exams or whatever, it makes sure that there are A's in the class. Not that we usually need to do that, but so, I mean, so the scaling factor will take that into account. And that's why, because we come up with a scaling factor at the end, that's why the total amount of point pile that you accumulate through the semester is like an arbitrary number. Like that's why we don't even care if it's less than 100 or more than 1,000. It's just what it is. And then we divide everybody's by the same amount so that we basically make up a number so that basically everybody ends up getting about, on average, about 8 or 9 extra points on their average from all the homework. Because, let me put it one last final way, what that actually means, and I'm not exaggerating, when I say that you get like 8 or 9 points on average, I mean just like the middle people in the class will get like 8 or 9 points on their average from all this homework. It's deliberately designed so that your grade would change like 3 half-letter grades from all the homework. Like if you thought you had a B minus just based on exams due to all the homework and participation you do, you wouldn't have a B minus. You would have like at least a B plus, if not an A minus. Like that's the idea. So yeah, so the 200, 250, please don't worry about that. It'll still work out in your favor. It's all meant to work in people's favor. I promise. I would not. The thing you'll find is that I fall behind. Okay, that's a big weakness of mine. I fall behind, just like some of you might fall behind, and that annoys people. That will annoy you. But anybody who took this, and that annoyed people last semester. And it is not cool that I fall behind. What I won't do, what I'm not doing is deliberately looking to screw anybody in grades. I think also if you talk to people from last semester, I hope, or I think you'll find that that's true. I have no limit in my mind to how many A's there could be. If everybody got an A, I would be happy. It would not be a problem. Like, and I don't need anybody to get an F. It's like for whatever it's worth. So the whole, and I think exams can be super stressful experiences that can really misrepresent certain students. Flip side, quick, as long as I'm talking about all this, and then there's still some stuff in the chat I want to get to. I want to get back to the physics. Flip side of all this, by the way, if you're finding this all very complicated or very annoying because you just like want to take your exams and not get all bogged down in all this and move on in your life, I can respect that too. So understand the flip side of everything I'm saying is if you get a 90, if you get a 93 on the midterm and you get a 93 on the final exam and you have an A in lab, which you probably do if you're getting 93s on the exams because the exams are not easy. But if you get a 93 on the midterm and a 93 on the final, and you have an A, and you have a 93 average in lab, then you're getting an A in the class, period. Like, period. Even if you never did one stitch of homework and never participated once in the Zoom. I mean, assuming I don't think you cheated, just to be clear, like all of this complexity is to pad the situation so that exams are not the only way to do well in this class, but they certainly are a good enough way. If you just want to take your exams and, and move on with your life and not get involved in all this, that is totally also respectable. It just doesn't usually work for that many people. So we have a more complex system. But that's why all of this stuff is technically like, it's almost like extra credit, right? You're not being punished if you don't do the homework. I just think it's ultimately an unsafe idea. But especially if you already know all this material or something from somewhere. All right. So it's just, the point is there's more than one way to get an A, hopefully, in the class, and more than one person will get it. All right, let me go. Sorry, I'm just getting, so the homework, what am I planning to get exams? Oh yeah, no. So hopefully by accident, I hope I just answered something that is in the direct chat. There, it says in the direct chat, I'm not going to read the whole thing, it's direct, but it does say in the direct chat, someone wrote, I know there are some professors who don't give A's at all. Okay, yeah, that is true. I know that too. Now, some of them would admit it and some of them would deny it. Some of them have a rule, like some of them do everything in their power to make sure that there aren't A's. Others of them, that's not their goal, but it just works out like that. Okay, I'm telling you right now, that is not my philosophy. I have a lot of weaknesses. There are a lot of things that are going to make this class hard for some of you already, just accidentally, because I'm human. Like, I'm disorganized and I'm messy about a lot of things that will already, and physics is already hard. I do not set out to prevent anybody from getting an A. I want people to get A's. I don't want people to cheat. And we'll talk about that when we get close to the exam. I want people to earn their A's, but people get A's in my classes. And you could talk to the people that took 203 last semester with me. I hope they'll confirm that, okay? And I'm not saying that to brag. Like, obviously different professors have different philosophies on this, but yes, it is totally, if you do all the homeworks and if you do all the homeworks and all the participation and everything, and you actually take the exam seriously, you probably will get an A in this class. That's the hope. You don't have to be a genius or or kill yourself, but you do have to do everything. Yeah. So that's just to answer something. Oh, okay, cool. Okay. No, I mean, because I've been on both sides. I mean, school is hard enough. All right. So wait, there was a question. All right. I do want to get back to the material. I definitely do want to teach you something. But early on, someone's been very patient here. It might have even been the same person. Someone's been very patient in the direct chat. Oh, yeah. Okay. Someone asked way early on, before I got involved in all this, that on the regular, like on the physics homework, as far as losing points, or if you didn't get the full points, why is that? And they asked, and this would probably apply to homework 1, because it's really all that I've given back to most people. If you didn't get the full points, first of all, again, it's not because you didn't have correct final answers. It's because you didn't do something procedurally that I'm asking for, which mostly involves being very, very step by step in showing your work process. That's also why it takes me a while to get these back sometimes, because I'm looking at step by step process. I need you to start by making the question. Well, first of all, I need you guys to do the homework on separate sheets of paper, not on the actual like PDFs that I'm giving out. There is no room to think or write properly on those. Like, so it's all like blue book type philosophy. Take out your own paper, fill out stuff on your own paper. On every question, make the question clear to me in your words. Don't screenshot my questions. Don't verbatim repeat my question. Summarize, like put a number like 1 and then summarize, put a diagram and then say like X equals 5. What is V or something? Just make the question clear. Then start with definitions or general principles or general laws. Then do steps, do a bunch of work to apply or algebraically manipulate those laws. Then fill in the numbers on the last few steps. Then get a numerical answer with units and circle that final answer. Like that's the whole basic deal that I'm looking for to get all the points. Again, if you lost any last time, you can resubmit. Abbreviations that I use. This is really what the direct chat is asking. Abbreviations that I use if I'm marking up the homework and you have lost points, the main abbreviations I use are, if I write WIQ, that means what is the question? This is a very idiosyncratic thing of mine. I know you don't have to do this in other classes a lot, but I want you always to make the question clear to me first before doing anything else. Even if you think I know the question, even if you think I've got the sheet in front of me, which I may or might not, even if you think I wrote the sheet, which I did, still make it clear to me that you know what the question is first. So WIQ means what is the question? And that's just a big physics research habit that's really important. But so WIQ means what is the question? WWW means what, why, where from, basically. It means when I write WWW, it generally means that you've put down an equation or a formula that might well be correct, but we haven't said yet in class. It doesn't seem to derive, it doesn't seem to be a first principle. It seems to be a derived equation that came from a bunch of thoughts or a bunch of steps. And I need to see what those steps are. I need to know why that equation is true or where it came from. So usually I write WWW when I think you've put down something that came from the web, which is fine. It's not cheating, but you can't just grab things from the web and write them down just because they're on the web. Like you have to show why they're true or how they derive from anything we've said in class. So WWW means like you got to show a lot more work to put this in context. And then the other abbreviation, if I write WWD, that means we will discuss. So that probably means you probably did make a mistake. It probably does mean, or you're incomplete or you haven't finished it or whatever. It means something's not right yet, but it probably means that it's such a common thing that, or you wrote like, I don't know how to do this or something. And if I write WWD, it probably means, yeah, okay, I get it. I understand. And thank you for acknowledging the question. Thank you for being honest. But since we both know that you're not quite there yet, I'm telling you, we're totally going to go over this in class. You're not alone. Tons of other people didn't get this either. So WWD means like hang tight and pay attention. Like I'll go over this in class. So that's WWD. WIQ is what is the question. WWW is what, why, where from. And those are the big ones that I can remember. Okay. Hopefully this, again, I know this is all, okay. Is that everything? Oh, all right. Last question in the chat. And I don't mean to cut these off. These are really good questions. I just know that we need to get to the material. Someone asked in the direct chat, is the stuff that we learn here applicable to the MCAT exam? That's a very fair question. And if we have time, we could talk more about the MCAT. I mean, the whole MCAT deal is a big deal. So the quick answer is yes. Anything you learn here is applicable to the MCAT exam. In my experience with colleagues and with former students, my experience is once you go through all this physics, if you're taking the MCATs, any physics that you do see, any physics on the MCATs that you recognize from class, you're going to do very well on. We go a lot deeper than the MCATs goes with the physics. So any physics that crosses over at all, and all of this does, yes, you'll know super well. But I also have to warn you that there's a lot of physics on the MCATs that we don't cover here. so basically this is about depth, not breadth. So anything we do here is on the MCATs, yes. And if you're paying attention, you'll hopefully know it. People often do really well on the physics part of the MCATs if they study, because what we're doing here, you'll know how to answer a bunch of questions even if you haven't seen them before from the way we're doing things here. But there will be physics stuff on the MCATs that we don't cover here at all, and you know that's just the reality. But okay, okay, wait. Oh, yeah, okay, wait. I would like to move on. I mean, these are fair. I see another question in the direct chat. I mean, on homework, um, everything I've been sort of saying with those abbreviations and all that is about homework, not exams. With exams, there's very direct point values. Like this thing is worth this many points. This thing is worth this many points. And if you don't do all the things and you don't get the correct answers, then you lose those points. And it's very like traditional percentage kind of thing on exams. On the homework, to be honest, right, it's much more impressionistic. Like I'm writing all these abbreviations and stuff. And if in the end, impressionistically, holistically, if I feel like you've left out a lot of steps, I will take off like about 15% or 20% of the points. It's not a direct formula. It's not, and I don't necessarily mark those points while I'm going. Like I make the comments, and then I make like a holistic determination at the end. Generally speaking, the score that you'll get on the homework will be very similar to many other people's scores. Like if I see a trend that lots of people are leaving out question 3 out of 5 questions, then I'll give like a very common 220 out of 250 or something like that. But it is holistic like that. It's not a formula or a direct thing, partly because the point is whatever points I'm giving you on the homework, I'm telling you, like, if you don't like your score, just look at my comments and redo it, and then you'll get a full score. Like it's all like drafts. So and I'm trying to go somewhat quickly. So it's more impressionistic and holistic. Just if you don't get the full points, look at my comments and try to resubmit. But I think if I get back to going over this, you guys will see more and more clearly. And right now, I think everybody's doing totally fine on the homework. And last thing, please also remember, of course, all this is recorded and posted on you. Hopefully you're seeing that these classes are posted on YouTube at night, and the PDF of all the notes we take are sent to your Google Classroom right afterwards. And partly I rewatch the YouTube to see how bad they are or whatever. And I spend a lot of time talking about this stuff, and it probably bores the garbage out of people, like how long I spend with this one screen up and not getting to the actual nitty gritty. So I think I'd like to do that now, is get back to the nitty gritty, and you'll see this just more and more as we go. Just the rule of thumb is just remember, you're not actually competing against me. Like you're not. We're both trying to get you to get an A. And I mean that honestly. I wouldn't lie about that. It's more stressful for me if you don't get an A. Okay. So any feedback I'm giving you is like an attempt to say, this is what you need to do to get an A. So if you didn't get a full score last time, like do this and then you will. Okay. I'm not trying to stand in your way or play hide the ball. It's not like that. Physics is hard enough. We together are competing against physics and against the world to try to get an A in this class on it. So like when in doubt, just assume, if you're confused about something, just assume there's still a way to get an A. And if you don't know what it is, you can find it out. It's not that I'm deliberately hiding it from you, if that helps at all. Okay, but I'm going to go back to question 9 now of the homework, because I just feel like I'm probably bored. It's 2 o'clock. All right, you can still ask questions while I'm going. I promise. I promise. I just want to get more concrete. So here we are. So we are. Oops. Okay. But please do have, whether you did it or not, please do have homework out in front of you. I mean, it's in, the thing on the screen. Have it out in front of you and know what I'm talking about. Okay, just reminding you what the situation looks like. The situation looks like what I just drew. Oh, also, sorry. And I hope I've answered all the questions in the chat. If I haven't, you could put in the question back in the chat again. I think I answered them all, but if I didn't, I apologize. Just put it back in and I'll see it. But all right, I just read you the picture. We're on question 9. And I'm going to back up a little bit on it. Technically question 9 says, or even here, let's even do this better. Okay, technically the last question of the whole sheet says when the clock strikes 1, when it's 1 second into the game, into this experiment, where is the mass, right? Now so technically, ultimately, we're looking for a numerical answer here. Ultimately, we're looking for a numerical answer. In fact, I think for those people, I think the answer that we're going to find is 0.116 meters, I think, but that's not really the issue. The real issue is we're looking for a general procedure for how to find X given T, right? What we're really looking for is X as a function of T, right? We're looking for a way to relate one to the other such that whether you plugged in 1 for T or 2 for T or 3 or 3.7, you could spit out an answer for X. That's what we're really looking for here. And if we can get that, then plugging in numbers at the end will just be a detail. Hence, I've rewritten the diagram basically with no numbers on it. I mean, there's some zeros, but I'm trying to remind us, we just, in general, we have a mass of M on a spring of stiffness K. And where the spring is normally at equilibrium, we're calling position 0. And where the mass starts off in its oscillation, we're calling X naught. And that's the place where it has instantaneous velocity of nothing, of 0. Like that's what I mean by X naught. When we asked all these prior questions 1 through 8, all to get a general predictive picture in our mind of what this motion's look like. Someone's joining, sorry. Of what the motion's going to look like, and now we're asking some specific some specific analytical questions about that motion. One thing, all those questions 1 through 9 or 1 through 8, we're all trying to establish that the motion is going to be cyclical, periodic. It's going to conserve energy. Like that's what we were trying. We looked at all these patterns of velocity, of acceleration, of energy. The summary of this type of motion that we're looking at so far, what we know so far is that this motion is oscillation, as in it's back and forth, periodic repeated motion. Ultimately, I'm ultimately going to call this motion harmonic oscillation. And yes, ultimately, that's a term you can look up on the web and you like, but we haven't established that yet. What we know so far is, hold on. So what we know so far is that the motion is oscillation, which in informal terms means back and forth motion. But what does that really mean? It means that it's cyclical motion. It means that this object is going to start somewhere, like in general in physics, if I ever say oscillation, I do mean what you think. It's not supposed to be a trick. Oscillation means the same thing as like an oscillating fan or an oscillating dance or an oscillating strobe light. Oscillation strictly means back and forth, which strictly means cyclical or round trip motion, means that some more people coming, sorry. Oscillation means that something starts in a certain position, goes somewhere, comes back to that original position. Like oscillation always involves some kind of round trip, even if there's no actual roundness. Like you might not actually see any curve in an oscillation, but yes. And so, right, that's good. What Caleb's putting in the chat. So what oscillation really means is periodic motion or cyclical motion, motion that gets back to where it starts over and over and over again in some repetitive, what he wrote, periodic, yeah, and therefore has like a period of time it takes to do each cycle. And that much we already know is true of this motion. How strictly, perfectly, or evenly oscillatory or periodic or cyclical it is, we also believe certain things. I mean, we know it is because we think its energy is conserved, but yeah, in general, we know this thing is an oscillator. We're gonna ultimately find that it's a very specific kind of oscillator called harmonic, but we haven't actually said that yet. But yes, exactly what Caleb said. Yeah, it's periodic, totally. That's awesome. Okay. So we're looking for x as a function of t. What we said yesterday. Well, we got this. Okay, I'm going to quickly summarize where we were yesterday. I mean, last Wednesday. We said this. So again, we want x as a function. That's what that's like lowercase f means in script, the way I write it. X as a function of t. What do we have so far? Well, we knew this. I'm just going to remind us. We wrote this. We wrote this. So we said so then we said again, this is just a summary of where we were on Wednesday. So we said this. And then I just rearranged it to make it, to isolate the derivative, basically. Okay. This is not an answer. Okay, we're looking for x as a function of t. What we just arrived at was not that. Like, we are totally not dumb. That's why we're talking about it for so long. What we arrived at was d2x dt squared equals blah, 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 x. We were looking for x as a function of t. That is, we're looking for some kind of function that has t as the independent variable and x as the dependent variable. We have something that we have. Sorry, those colors are bad. 1 second. We have an expression that only has two variables in it. And the two variables are x and t, which is what we're looking for. And they are appropriately arranged variables. Like, I can just tell by the fact that x is in the numerator of that derivative that x is being treated as the dependent variable and t is the independent variable. So that's a very good thing. Like, we've landed at an expression that is treating x and t properly, and everything else in this expression is a constant. So we have the information we're looking for, but it's arranged in a very strange package. Okay, again, we're looking for how x depends on t. What we have here is the second derivative of x with respect to t is related in a certain way to x. Okay, and so what we have here is a differential equation. I need to show you what to do with that. Like when physicists first landed on this, and when Hooke was doing Hooke's law in the 18th century, and he landed on this, there was no class called differential equations or something that he could just take, or some book. He had to like unpack this and deal with it the same way we're going to unpack it and deal with it right now. Um, Okay, now here's this very important point. This is where I have to dwell. This is like pretty much, well, we're almost up to where we were at the end of last Wednesday, where I guessed something about cosines and stuff. Here's the thing I want to alert everybody to, and this is where homework 2 comes into play. What the beginning of homework 2 is meant to try to have you see in practice is this idea that I'm about to say right now. I'm saying we want x as a function of t. We weren't given that. We were given instead some derivative of x with respect to t. Now, you might say, if you've been taking math classes and doing your job as a calculus student, if you have like some background of familiarity, you might say to yourself, oh, he wants the function, but instead he has the derivative. So what he should do, Yaverbaum, or what we should do is just go backwards. Like if I have the function and I want the derivative, then I differentiate. But you might say, but if I want the function and what I have is the derivative, I should undifferentiate. I should backwards differentiate. I should inverse differentiate. Therefore, I should integrate. If you're thinking anything like that at all, if you follow what I just said, then you're thinking very well, and you've definitely been doing your homework, and you've definitely been participating in other math classes, and that's good. But I'm here to tell you that's not good enough. Like that is good if you follow what I just said, or if it even ever occurred to you, then you're in the right place. But actually, the situation is harder than that. And that's why we're dwelling on it, okay? And here's why. What you would just integrate, we would just integrate if what we were given was a fact about some derivative of x. If we were told that the derivative of x depended on t in some way, depended on the independent variable, then we would just undo that with an integral and we'd be fine. Or in this case, since it's a second derivative, we would integrate twice. And that might be annoying, but it would work and it would be fine. But that's not what we have here. What we have here is that the derivative of, we have dx dt twice is some function of x. And that is a game changer. That's what makes this thing a differential equation. It's not just an equation with a derivative in it, which is what I used to think, that's what I assumed differential equations were going to be, a bunch of equations with derivatives in it. No, a differential equation, this thing is slightly more exotic than that. So by way of contrast, or to actually show you what's going on here, I'm going to take a sidebar. And this, again, if you start, or when you started homework 2, or when you start, you'll see in a way that this sidebar will look familiar. But okay, so in a moment, I'm going to flip the page and I'm going to invent a smaller, simpler problem that is not the problem at hand in order to show us something about what to do with the problem at hand. And that's what physicists do all the time. Again, problems are big. We break them down into smaller things so we can figure out how to do them. And especially if we're actually, for the first time, making up how to do a problem because we're research physicists. All right, so I'm going to flip the page. Tell me if you need me to flip back. But I'm going to say, consider, okay, so this is a sidebar problem, like to get us to the actual problem at hand. Okay. Now, often, to be honest, also often, again, when you do homework too, or if you've done it, you'll sort of see a relation here. Often, if this were a longer class or this were during the fall or we didn't have COVID, I would probably pause right now and have you all do yourselves what I'm about to ask. And it probably would be better for you. And if you're getting bored, please just try it on your own. But in the interest of time, I'm just going to do it. By it, I mean this. Well, actually, I'm going to say 2 seconds. Okay, so here's my sidebar problem number 1. I'm actually going to do 2. Here's sidebar problem number 1. Say we're just like walking through the forest and we stumble on and we're looking for x as a function of t, because that's kind of always our point in physics. Okay, and that's also how this relates back to the actual problem at hand. Say we're looking for x as a function of t. We're looking for some rule that relates space to time, which is really what we're always looking for in physics. And we're walking through the forest, but we don't know what x is a function of t, but what we're told by someone is, oh, dx dt equals 5t. Like someone tells us something about a derivative of x with respect to t, and they relate it to t, and they tell us that fact. And they even also tell us a fact about initial conditions. Like they say the very first value of x is 7, right? That's my second given there. They say the value of x when t is 0 is 7. That's another way of saying x naught equals 7. Same thing, right? So that's one fact someone gives us, let's say. And they also give us this other fact that the derivative of x with respect to t is equal to the function 5t. Our goal is to figure out x as a function of t. What we would do here in this situation is we would do what I think many of you think we would do. We would use integrals. And so if you're thinking that, you're right. Like here, we're looking for x as a function of t. We don't have it. We have a statement about the x derivative. So we unpack that. We invert that. We work backwards on that by doing an integral, and we get what we're looking for. But here's how, if we're careful, because we can't just like randomly do integrals just because we feel like it. What we do is this. What we would do, we would say, I'm probably going to go on the other page in a second. We would look at that first statement. We'd say, okay, dx dt equals 5t, right? So what we would do, and I'm going to do this on the other side, we can't just like integrate that. Like you never see integral sign dx over dt. Well, anyway, what we would do is this. We would say, okay, therefore dx equals 5t dt. Okay, we would multiply both sides by dt because we can, because a derivative is a ratio of differentials. Like some of you might not realize that we can do this, or it might seem funny or whatever. A derivative is a fraction. It's an infinitesimal rise divided by an infinitesimal run. We would treat that derivative like a fraction, multiply both sides of the equation by the denominator, okay? And we would have dx equals 5t times dt. Then I'm going to the other page. I'll just rewrite that. Again, you can always tell me to turn back. Please do if you need to. But I usually try to recopy the first line. Okay, so we have this now. Now, now we can integrate because because you can't just like randomly integrate because you feel like it, but you can always do to one side of an equation anything you want as long as you do the same thing to the other side. Well, I can now I have something that I can integrate both sides of this equation because I can go like this. And this is an example. Like I know many of you would think about integrating, but I'm adding extra clear steps here to show why it's actually justified to integrate. Some of you might have skipped this step in your mind or whatever, and maybe you could even get away with it and get the same answer in this case. But then you're going to see when I go to the other case why this extra step makes such a difference. So I multiply both sides by the dt. Now I have an equation that has differentials on both sides. And you'll know, like, even if some of you are still not totally comfortable with integrals, which it takes a while to get comfortable with them, but if you've done integrals in a math class, you know they never ask you to integrate 5x. They ask you to integrate 5x dx, or they never ask you to integrate 5. They ask you to integrate 5 dx. There's always a d term in the integral, and there's a real reason for that. But even if you don't totally accept yet or feel comfortable with the reason, you know it's true. There's always a d term in an integral that tells you what the actual variable is. And if there isn't, it's not valid. And what you never see is like integral of dx over dy. Like that doesn't make any sense. And so that's why I couldn't just integrate this thing a minute ago until I arranged it. Now I've got an integral on both sides. That's legit. It's two different variables of integration. These are both indefinite integrals, right? Like I don't know what the boundaries are of these. I don't have limit. Oops, I'm sorry, someone's joining. And that's okay. So I'm going to treat them, but I now have an indefinite integral on one side and I have an indefinite integral on the other side. So now I do them, right? On the left side, the integral, maybe someone should shout out here. I'm almost a little nervous to do this, but the integral, and just pretend this is a math class now. Like even if you don't know what this physically represents, if you have the integral of dx, what is that if this were a math class? Like what should I put on the left? And you could put it in the chat for tons of points, or you could shout it out. But what should just to make me feel human, what should the left side be? Like, awesome, yes. So Avery Eller, yes, it was public chat. So you wrote x, and I totally agree. The integral of dx is x. And I'm also going to go one. So thank you. That's awesome. And by the way, I'm going to pause here for a second. I don't want to, well, actually, yeah, I want to say something about the fact that he put that in the chat in a moment, like a compliment, but I'll finish this before I do. He's saying, Avery Eller is saying that the integral of dx is x, and that's correct. I also want to point out that this is an indefinite integral, right? Just because it is, because like I don't know what the boundaries are. I just like wrote an integral sign in. So technically speaking, if this were a math class, I would have to say something like x plus c, right? There would be an arbitrary, and you never know how technical anybody's going to ask you to be, but I am being technical here I have to. So I'm going to say x plus c because that was an indefinite integral. So I get the arbitrary constant, right? I mean, I think you all know what I'm talking about. Oh, yeah. And then on the other side, yes. Wait, is that a rule for me? Well, yes. The integral of dx, yes, we'll always, sorry, I'm looking at the direct chat. It says, is that a rule for every time we have the integral of dx? Yes. I don't know if it's like a rule, or if it comes from rules, but you certainly can depend on it and memorize it or whatever. The integral of dx, the indefinite integral of dx is always x plus c. Yes. Yeah. Then on the other side, now slightly more tricky, it's the integral of 5t dt. Also an indefinite integral. So it's also going to get a different arbitrary constant. Does anybody, and I do again want to compliment Avery Eller and, well, anybody else who put something in the general chat about this. I want to be clear about points about that in a moment. But does anybody want to, well, actually, I'll pause right here and say, so anybody who said hello today can certainly submit that for 50 points, including Avery Eller. And I'm not trying to single him out. I just want to make a point. So like Avery Eller participated today because he wrote X. So he could submit that, screenshot or whatever, remind me, say, I said X when you asked the integral, and submit that for 50 points. But there's also another portal that appeared that I want to explain. Another portal for homework points appeared today, and it was called something like for right or for wrong. And that's a portal that you can use for participation points anytime any of you put something in the chat or say something that is subject to being right or wrong. Like, in other words, anytime you take a risk. Like, it happens that what Avery Yeller wrote there, I'm saying is right. It is right. So yay. But even if I thought it was wrong, if he put in Y, but the answer is X, and then I hopefully politely said, no, I'm sorry, that's wrong. Either way, he wrote something that lends itself to being called right or wrong. He took a stab at something. Either way, therefore, he can screenshot that or remind me of that and put it in the portal that's for right or for wrong. And that one's worth like 75 or 100 points because it requires guts. And what I'm trying to say, and by the way, he can double dip. He can put in that, and it's not just him, it's like anyone, but I'm just using him as an example. He could put in that X as an example of participating today at all in the 50-point portal, but also that exact same thing. He can double dip and should double dip into the portal that it applies that's called for right or for wrong. Because not only did he, because unlike hello, like hello is 50 points because thank you for saying hello and thank you for real. But hello is not right or wrong. It's just a greeting, right? Like there's no way I could say yes or no to hello. So writing in X in the chat is going an extra step forward. It's actually having the guts to set yourself up where the professor might even say you're wrong and might say that in front of everybody. And nobody likes that. Hopefully I'll be polite about it. But we all know that takes guts. So I'm saying anytime you write in anything that could be right or wrong, I don't care whether it's right or wrong, you're getting 75 points for it if you remember and remind me in the portal. That's what that portal's for. And if you want me to make more of that portal, I will. Okay. And this is the same thing with everything else. If you put a screenshot in if you share a screen of your work, that counts as regular participation, but also double dip it in the screenshot portal. Okay. Again, it's like Nook Miles in Animal Crossing, if that means anything. It's just whatever, or it's like Google labels rather than folders. Like anything that applies, and you can apply it more than once. I want you guys to be in the habit of trying to do things that someone could say they're wrong. I want you to view wrongness as just as valid as rightness. That's like the secret message. It's not secret. That's the underlying reward system here is rightness is just the flip side of wrongness. And they're both about progress. So anyway, the left side is X plus C. Does anybody want to take a stab at the right side? Like what's the integral of 5t dt? If this were a math class, if t is the variable, in other words, does anybody want, if no one does, I'll move on, but does anybody want to try the right side? You could say
it's 5t squared over 2 plus c.
Awesome. Totally right. 100,000,000 points. Yes. Thank you so much. Exactly. And again, I'd like to think that even if he got it wrong, I would be cheering for him just as much for having the guts to do that. But yeah, it happens that he's totally right. What he's saying, and that was Caleb, I think. Yeah. What he's saying is this, right? And he's just doing like the power rule backwards. And that's also a rule. I don't, some of you are more comfortable with integration than others, but yeah, the integral of 5t is 5t squared over 2. And then there's also a plus c. And now I'm going to say and so if those were two different math problems in two different math classes, one answer would be x plus c. And then on the next exercise, the other one would be like 5t squared over 2 plus c. But now, since they're in the same physics situation here, I'm going to add a modification. Now I'm going to say I can't actually call them both c, at least not for the moment, because they're not each one of those c's. And I'm not saying he did. This is not a correction of what Caleb, this is just me going on now. The right side and the left side each have an arbitrary constant. An arbitrary constant means exactly that, like a letter that represents that there must be some number there, and it could be any number, but we don't know what the number is. So there's no reason to believe that it's necessarily the same number on the left side and the right side. So to be careful or clear as a physicist, I better do something like this. Okay, again, this is not a correction. I'm just like moving on now and saying, so far what I have, if I'm solving this problem, and this is an example of a solving for a function when all you know is the derivative, like this, I'm still in my sidebar land here. If I were solving this sidebar problem, so far I would have this, okay? And remember, it's easy to lose sight. Even in this sidebar problem, what I'm looking for is x as a function of t. So my goal is to isolate x and have all the other crap on the other side. That's my goal. And I'm getting there. First thing I'm going to, but this is what I have so far. I have x plus c1 equals 5t squared over 2 plus c2. Now c1 and c2, I don't know what they are. That's kind of annoying. It looks like right now there's two unknown things here, and I'm trying to reduce the number of unknowns. So the first step I'm going to do now, if I'm being really careful, I'm going to say something like this. Now, and you may not have done this before in a math class. Hopefully you'll see why it makes sense, but I'm going to say, remember, all right, like we're looking for x as a function of t, so they are the two variables. Everything else in my final expression better be known. Otherwise, I haven't really answered my question, right? And right now, it looks like I have two other unknowns, c1 and c2, so that's annoying. So what I'm going to do on the next page, I'm just rewriting. Again, I can go back, but what we have so far is x plus c1 equals 5t squared over 2 plus c2. The first thing I'm going to do is say, well, wait, I'm sorry. Right, I'm going to bring the C1 to the other side, so I've got x isolated by itself. But now I can say, remember, C2 and C1 were both arbitrary constants. In other words, a number that exists, but I don't know what it is, or it could be anything. So they're not necessarily the same, but I don't know what they are. So what I can do as a trick is say, and I named them C1 and C2. I could name them D1, D2. I could name them C and E. Like, it doesn't matter what they're called, right? So why don't I do this? I can say, let's make up a new number called C3. And C3 stands for the difference between C2 and C1, right? And then by that trick alone, I just reduced the number of unknowns. Like, I had two unknowns, if I'm being fair, but now I'm saying, apparently, like, the difference between those two unknowns is what I have to worry about on the right side of this equation. So I'm just going to give a name to that and call it C3. C3 is the difference between C2 and C1. And then if I do that, there's only one C in the whole thing. So then I can do this. It all seems very roundabout, but it's a step that's important for things when we don't know what's going on. So now that I took the two C's that I didn't know, so one number might be 5 and the other is 3. So then C3, one number might be 8 and the other number might be 6. So the difference between them is 2. And I just called that C3. But now that's the only unknown in my whole situation. So I don't have to call it C3 anymore. I can just call it C. It seems like I'm going in circles, but it's a tactic for cleaning up and combining and reducing the number of unknowns as you go throughout a calculus or a physics problem. So now what we have is this. We're almost there. We have an answer to this. X equals 5t squared over 2 plus c. That's almost an answer to the question that we're looking for in this sidebar. We're almost there, right? We're looking for x as a function of t. The only problem is it has a c in it, and c is unknown. And we don't want any unknowns in our expression if we're looking for a known answer. So now we have to solve for C. And some of you in the class may already either know a way of doing this, or you might see SEE, a way of doing this right now. In the interest of time, I'm just going to say it. Like if I want to know what that C is, remember the C was there because the integral was indefinite. If the integral had been definite, if we had known the boundaries of the integral, if we had known like the beginning and end conditions of the integral, then we would know everything and there wouldn't be a C. We thought we didn't know the end points of the integral, but we do know something else instead. Like we'd be stuck now, we'd be screwed, except there was one other piece of information given in the sidebar problem that we haven't used yet. And that's always a good technique on exams. If you're like down at this point and you're like, oh my God, there's still something I don't know, go back and make sure you've used all the information that was given. The one other information we have an arbitrary constant because the integral was indefinite. Whenever mathematical integration, indefinite integration, gives you arbitrary constants. Wait, let me put it a different way. The arbitrary constants that come from indefinite integration are always representations of or interchangeable with the boundary conditions of the physical problem. That, let me say it one more. What I'm saying is if you want to solve for an arbitrary constant that popping out of the math, look at the initial conditions provided by the physics. They are in fact one and the same. One way of saying boundary conditions in math is you give limits of integration. We're integrating from here to there. In physics, you say, oh, we're looking at a problem where the starting position was blah, or the starting velocity was blah. The conditions that are provided in a physics problem are the boundaries of integration in the math problem. They are one and the same. So, and if you have one, you actually have the other, whether you know it or not. So whenever you are looking to solve for an arbitrary constant that came out of mathematical integration, you look toward the initial conditions provided by the physics. That is a rule for anybody who's asking in the chat. You could totally, you may not understand the rule quite yet until I apply it right now, but it absolutely is a memorizer or an absolute rule that the constants of integration are the boundary conditions. The constants of integration in math are the boundary conditions of physics, like always. Again, that might be an abstract statement, but here's what I mean. In this case, I don't know what C is, but I look back at that other fact that was given at the problem. The other fact of the problem said the initial value of X, the very first position of this situation, whatever it is, the X naught was 7. That is enough for me to solve for C. How? Because I can say this. Well, here, I'm going to go to the next page. what we have so far is x equals 5t squared over 2 plus c. I believe that's what we have, right? Just checking. Yeah. We have that. We don't know c. But we also know that x naught, which is the same thing as x at the value of 0 equals 7. So what do? We just plug in 7 for x whenever t equals 0. We plug in 0 for t and plug in 7 for x and see what happens. In other words, 7 equals 5, 0 squared over 2 plus c. In other words, 7 equals 0 plus c. In other words, in this case, it's not that hard. 7 equals c. Right there, and I'm not saying it's always that simple. I'm not saying that c is always exactly.
If it's not here or on the wall, then no. We had a lot. I mean, it looked like we sold out actually. Yeah. No problem.
Maybe mute everybody. Okay. Right. So I'm saying here in this case, c equals 7. I'm not saying that c always equals whatever x naught equals, but I'm saying if you can always get c by knowing what x naught is. So in other words, so our final answer that's our final function. Hold on one second. One second. Okay. I want to pause for a second and say, wow, that's so awesome that Catherine is still showing video. Sorry, that's totally great. That's like a million points. Okay, sorry. Well, I want to say that this is the answer to sidebar 1. That was still sidebar 1. I'm going to do sidebar 2 and then go back to the homework problem number 9, believe it or not. That was an example where you're looking for a function, you're given the derivative. Like that was an example where you're given a derivative, but you're looking for the function. So indeed, all we actually had to do there was integrate and we got the answer. Like if you didn't do all the steps that I just did and you just sort of intuitively in your mind felt like you should just do an integral, you'd probably get the answer that I just got. I dragged it out to make my usual teacher point. But if you just stand back and look at it, basically I just took the original function and I integrated it and I got the answer that you would expect. That sidebar that I just did was an example of an equation that had a derivative in it, but I would not call that a differential equation. Okay, I'm trying to set up a contrast here and say that sidebar hopefully wasn't so bad. I may hopefully added some extra steps that you might think were unnecessary, but hopefully you followed what I did. Hopefully, and if you didn't, obviously tell me in private and there's no shame. But that's an example of me very carefully dragging out a process that I think is basically just integration, and I think you would expect. The deal was, the key point to that sidebar, the contrast, is that there on the right side of the original given thing, there was a t, not an x. Let me now show you sidebar 2 and show you that we're going to get a very different answer. Sidebar 2. Well, so hold on, sorry. Okay, again, at the risk of boring anybody or annoying anybody, everything I just did is meant as like a control in this intellectual experiment, so to speak, or a base case or something. If you like, everything I just did is not a differential equation. It's an equation that has a derivative in it. Okay, now let me contrast with sidebar 2. Oh, sorry. Okay. 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 So, all right. So now we're going to do very similar problem, like same goal. Goal again is we're going to determine x as a function of t. Again, that is totally the goal of that is the goal of question 9 in the homework problem. Really, that's what we're trying to study now is like, how do you get an xt function when like you don't know it? Here now, and here the setup looks very similar. Like we're again given a derivative of x with respect to t rather than the function itself. So, and we're given an initial condition. It's like a very similar setup to sidebar 1. The only detail that, well, there's 2 details that differs. One, I gave a slightly different initial condition for a technical detail that's not interesting. But the other, the major detail is, I mean, the major distinction between this and sidebar 1 Okay, notice now, so it's just a 1 detail shift. Instead of a t on the right side, I now have an x. And it almost seems, it would seem to me that that shouldn't make a big deal of difference at all. And in some ways it doesn't in terms of the procedure we're going to use to unpack this. In this case, we're going to use our same technique that we already figured out a minute ago, but it's going to make an extraordinary difference in the result. And it makes an extraordinary difference in the meaning of what we're saying. See, yeah, it's important to remember that independent variable is like cause and dependent variable is like effect. Like one yields the other. There is a reason they have 2 different names. And so here what we're kind of saying is like the rate at which some effect changes depends not on the cause, but on the effect itself, right? There, I want to make it clear to you, right? Like, in other words, this thing that we're about to deal with now, this, because of this fact alone, the mere fact that what's on the right side is x rather than t, means that this is now a differential equation, not just an equation with a derivative in it. Like, it actually makes that much difference. And it actually makes that much difference because there is real distinction between x and t. Like, sure, you can always twist your graphs around. Like, in the end, we can call anything whatever we want. But once we're looking at derivatives and once we're measuring a rate of change of one thing with respect to the other, we have tacitly decided which one is depending on which direction the cause-effect relation goes. So here in this case, we're saying we have some situation where we want to know, like, how position depends on time, for example. And what we're told is that the rate of change of position with respect to time, in other words, like, say, velocity, we're told here that velocity doesn't depend on what time it is. It depends on where you are. And that's sort of circular right from the get-go, because where you are, we generally think of as something that depends on your velocity, if you follow me. So this is a different situation. This is a differential equation, literally just because what's on the right side is x, not a t. And if we were talking about dy dx's, then if what was on the right side was a y, it would be a differential equation. Okay, what are we going to do? What I'm going to do is I'm going to, like, so if I just took the integral of both sides, if I just took the integral and said, oh, the integral of 5x is 5x squared over 2, that would be wrong. We have to carefully unpack this the same way we just did a moment ago. Like, if we go step by step, we'll see what's going on. Okay, so we're going to go step by step, just like before. We have dx, I'm sorry. We have dx dt equals 5x. Okay, so I'm going to multiply both sides by dt. I'm going to say dx equals 5x dt. Okay, so now look at that. Now I have like d's on both sides, but I can't just integrate both sides of this, because the integral of 5x dt doesn't make any sense. Like they're two different variables. So I'm going to collect all the like terms, like they already were collected in the other case. In other words, so I'm just going to recopy again. So I have, and if you want me to go back, I will, but I have dx equals 5x dt. So I want to collect all the like terms. So I'm going to say dx over 5x equals dt. In other words, right? In other words, right? So now I have something that I can integrate, but it is a very different. Oh, and in fact, let me go one step further. Sorry, I probably should have done this, or this is sort of silly, but what I can really say is, right now I have something that's clean and straightforward and proper to integrate on both sides. Very different integrals from the one that we had in sidebar one. But now this is right. So I'm following the same procedure, but I'm seeing something different. So let's do this left and right. Like, so now I'm going to integrate both sides. Right, so I'm just going to recopy again, and I'm just trying to be clear, so I'll recopy again on the other side. Tell me if you want to go back. So we have 1 over x dx equals 5 dt. I'm going to, right, that's what I have. So I'm going to integrate both sides of that indefinite integral. Okay. So if anybody now anybody know what the integral of the left side is? And you can say it. You can put in the chat. You can also not. But does anybody have any thoughts about the left side of this? Oh wait, does class end? Oh, class ends in 55. Okay, yeah. Anybody? Any thoughts on the left side?
You mean, it's Elena X, right?
Exactly, exactly. Beautiful. Yes, that's awesome. Thank you very much. Right. So the left side is right, because so to everybody, it's the integral of 1 over x dx. And again, like, and I am pulling from math now. Obviously, the more comfortable you are from a calculus class, the more comfortable you are. But notice, so, but what makes it math is that I'm thinking of x as standing for position, and I'm thinking for t as standing for time. But it doesn't really matter, right? As long as they're just variables, then these mathematical rules apply. So yeah, the left side is natural log of x, and we'll put in an arbitrary constant there. That's awesome. Totally. Yeah. A very different kind of function, right? Like now suddenly we're in the land of these like more unusual, what are called transcendental functions. At least on the left side we are. But now, and then somebody else or anybody on the right side, what do we get? So I'm wondering if any, so in other words, what I'm asking, and I'm not trying to put pressure on anybody, but just to, and I can go back to the other page if it's helpful, but on the right side, we have the integral of 5 dt. It might actually, this might make it simpler if I go like this. I'm allowed to do this. I don't know. And then you can look back in your notes from the first example, but any thoughts from anybody on what's on the right side? In fact, I'll even do this. Oh, sorry. I didn't even look at the chat. Yes, that is awesome. Yes, Kirsty. And I totally appreciate that it's somebody new, at least I mean new for today. Yes, totally right, Kirsty. And I don't, wait, I'm saying Kirsty because I'm thinking you. Yes, you were in the public chat. Whew, I almost outed you there. Yes, totally awesome. And also thank you for, I know we're now in that realm where I'm sure I'm losing, I'm sure it's hard to keep paying attention. So thank you for anybody who still is. Yes, what Kirsty put there. So what I think it was Caleb or Jacob said for the left side was totally correct, and then what Kirsty's saying for the right side is totally correct. So it's this. Okay, so this is what I have so far. So I'm following the same procedures as before, but I'm getting a very different type of answer. I'm going to do that. I'm going to start skipping steps now. Like I'm doing the same thing as before. Well, I'm not going to skip. I'll do the steps faster now. I'm going to say again, like, okay, and I do this all the time in physics. So I'm going to more and more, as you get used to this thing, I'm going to do it in fewer and fewer steps. Oh, sorry. So we have this. And notice again, if this were just a math class, or you were just if you were, I mean, this is where physics, and again, I'm trying to be somewhat clear, trying to be somewhat step by step, but I am also trying to get faster and faster and thicker as we go. I mean, if you were to stop, if you weren't paying attention for the last 2 hours, and then you just swooped in right now and just saw this board right now, and just saw where I wrote let C3 equals C2 minus C1, and then you just saw where I wrote let C equals C3, like that almost doesn't look like it makes sense, or it almost doesn't look like it's fair. Like, what do I mean let C equals C3? But I'm trying to say that these C's are all arbitrary constants. They are just letters standing for numbers that we don't know. So when you realize that, it means that it doesn't matter what you call them as long as you call them something consistent. So therefore I can play these games. All right, so I'm saying the natural log of x equals 5t plus c. That's what I have so far. I'm going to go to the next page now. Again, you could tell me to turn back, but I'm saying natural log of x equals 5t plus c. What was I doing? I was the whole time looking for x. I'm looking for x as a function of t. So I want x by itself. So I'm going to do the natural log backwards, right? I'm going to do the inverse function of the natural log. That is to say, I'm going to raise e to each side of this, so to speak. I don't know how you say that, but I say this, in other words. Right? Now look, and we're almost done, but let me again pause. And again, I apologize to anybody. For some of you, I'm sure I'm going too slow. And for some of you, I'm sure I'm going too fast. And let's just admit that to ourselves and not have shame in either one. And I apologize to both of you, but like, obviously it's a class, so if I'm going too slow, you can privately chat. You can say, you're going slow for me. It doesn't mean I can speed up right at that moment, because there's other people in the class too, but you can let me know that in the private chat, because if enough people do, I will adjust. Or just if you just want me to know that that's true, you can. On the other hand, if I'm going too fast, you can privately chat that, or please ask a question of where you lost me, or just say, can you pause for a second, please? Really, like all of you, it is a class. It is for you, not for me. I mean, in that sense, because why I'm pausing right now, all of a sudden I have x equals e to the 5t plus c. I want you to recognize that I think all of a sudden the situation looks a little crazier than it did 2 minutes ago. Like even if you're sort of cool with integrals, or you sort of remember them from a math class, all I did from sidebar 1 to sidebar 2 was change one letter. But in sidebar 1, we were dealing with fairly straightforward integrals and functions, like, something times t squared over something. Now suddenly we got natural logarithms in our life, and I just undid a natural logarithm, and there's e in my life. There's definitely people in this room who are okay with 5t squared over 2, but are not okay with natural logarithm. And first of all, if you're one of those people that understands 5t squared, but is not thrilled about ln or e, first of all, I want you to not be ashamed of that, even if you don't tell me. If you're in your mind, you're thinking, oh shit, there's an e now. Don't deny that fact to yourself. It's okay. I've been there too. E is a lot harder than 5t squared. But also, let me say to everybody, that's part of my point here. All of a sudden, e's are popping up just because we changed a t to an x. Like, it makes that much of a difference. The kind of functions we're getting now are all of a sudden, they are harder functions, whether or not you're uncomfortable. Like, even if you are comfortable with e and natural log, it is definitely a more exotic, strangely behaved function that all of us learn later than 5t squared. So it should be noted that all of a sudden the math is getting a little crazier now, and only because I changed a t to an x on the right side. It makes that much of a difference. Okay, but that said, I'm going to go on. I mean, but please do let me know in the private chat or whatever, if you want me to go faster or slower. But now I have x equals e to the 5t plus c. I'm still looking for x as a function of t. I'm just about there because I have x by itself, but c is still an unknown here, and I don't want it to be an unknown. I want it to be known. So I got to solve for it. What's the easiest way for me to solve for it? Well, I'm going to use my initial conditions, but first I'm going to do some simplifications. I'm going to use this old E rule that some of you might puke when you see it, but I'm going to say this Like, again, that might be, I mean, just remember, in other words, well, it's a rule and it makes sense. And I can explain the rule on the sidebar if anybody wants, but just remember, like, it actually really does make sense, but you might have just memorized it at some point along the way. But that's what I'm using, that e to the blah plus blah is always the same thing as e to the blah times e to the blah. Again, we can talk about that on the side if you want, but it is the case. So then I'm saying, this now. I'm saying we have x, we're looking for an x function. X equals e to the c times, oh, someone's here, sorry. I'm saying e to the c times e to the 5t. Now, I still don't know what c is, but here's something I can do that you might think is outrageous. I'm going to do something now that's totally outrageous if you haven't been following this for the last hour and a half, or at least like taking notes or watching the YouTube video. Like, I'm going to now say, I'm going to say where I see that e to the c, I'm just going to rename it c. Now, that is totally illegal if it's out of context. Like, you can't just change the name of a, like, you can't just say e to the 5 is the same thing as 5. But c is a letter that stands for an arbitrary constant, right? C is a letter that just stands for some number that we don't know what it is, but is a number. Well, e raised to a number, put another way, any number raised to an unknown number is just some other unknown number, right? Like, it changes it. I'm not, in other words, technically, I guess what I'm saying is this. Like, I'm saying e raised to the power of c is e raised to some power that I don't know is some other new number that I don't know. It is a new number. It's a different number, but I didn't know what the first one was anyway. So I could call the old one C1 and I could call the new one C3. But if there's only one of them, I might as well just call it C. You see what I'm saying? Like, this is like actual logic. It doesn't, if you don't see the whole context, it might not look logical, but I think it is. And physicists and mathematicians do this all the time. I'm not making it up. It's a standard practice. It just might not have come up in your life before, or maybe it did. But all right, so let C equals C3. So I'm saying, therefore, I'm saying, thus we now have X. Well, we had this. Actually, I forgot what we had. Oh yeah, we had this. So now we have this. So now we have a fairly simple, maybe not easy, but
can you go back really fast, Professor?
Absolutely, I would love to. And who was that? Juanita? Yes, absolutely. God, it makes me feel this thing.
Thank you.
No problem. If you never asked that, or if no one ever asked that, I would really be worried something was wrong. Yes, no, totally. Okay. But you're good. It's good now. Or
Yes, you can move on now. Thank you.
all right, cool. Thank you. All right, hold on. I'm maybe going to change that. Okay. Okay, so now we have this. So now we're almost at the end of sidebar number 2. We have X as a function of t. Everything else in there is a constant, but we don't know the constants. Now I think we can actually solve for that constant. Like, I think we said that, right? I think, yeah, like the other condition that was given in the problem. Therefore, and maybe it was stupid to make it a 1, I don't know, but we said, therefore, oh yeah, I don't know why I made it a 1, but it's okay. So I'm using that initial condition that we initially had that told us that when t was 0, x was 1. I'm not quite sure why I made it 1, but I did. So I plug in 0 for t, and plug in 1 for x. So we get and you know, e to the 0 always equals 1, or anything to the power 0 equals 1. So 1 equals c times 1. So c turned out to equal 1. Again, that's maybe kind of simple, but it's just the way it is. So c equals 1. Then our final answer well, we said okay.
Can you go to the previous page, Professor?
Yes. Hold on. Yeah. Hold on. Okay. Yes.
Okay, you can move on.
All right.
Thank you.
Thank you. All right. Cool. Okay. So now, just again to review, all I did, we're still on homework 1 here, everybody, and it's not your fault. It's mine. It's not a question of fault. It's where we should be. We just did everything I just did is in the effort to bring perspective to question number 9 of homework 1. We are still in the middle of the forest of question 9. Question 9 seemed really simple. It was just given t, what is x? But the facts that were, question 9 was just find x as a function of t, given f equals negative kx and f net equals ma. What I'm trying to show everybody in these two sidebars sidebar journeys that I took in the middle of question 9, I'm trying to show that if you're trying to determine x as a function of t, if what you're given is some facts about the derivative of x, and if that derivative is related to t, to the independent variable, then you don't have too big of a problem. It's okay. You can basically do an integral and you basically get a function that doesn't look too crazy. But if you have the derivative dx dt or something related to x, that means the rate of change is depending on the dependent variable. It means a rate of change is depending on a dependent. In effect, it means that a rate of change of effect with respect to cause is related to not to a cause, but to an effect. Like in English, what I'm saying is if x is on the right-hand side of some derivative equation, that leads to a very different kind of result from when t is on the right-hand side. In this case, for example, it leads to an exponential function, which for most of us in the room is a harder function to relate to than 5t squared over 2. Like most of us know t squared, like x squared or t squareds are like parabolas. A lot of us have been dealing with them in a lot of science and math classes, parabolas. But exponential functions are higher level, no matter where we are in math or science. Then they pop out, or higher level functions like this pop out when we have differential equations. Let me put this one. So I want that to be in the back of our minds when we go back to the spring problem, question 9, which I'm going to do in a moment. Just note one thing. Ooh. just note, when you have a function that's like the one we just got, like we happen to have had 5t squared over 2 or something, but just in general, if you have a quadratic function, like you might remember from physics 1, if you have like x equals 1/2 at squared plus v naught t, like all that. If you have a quadratic function, something that depends on the square of time, which comes up a lot in physics and which is true in free fall and all that. If you have some kind of x equals blah t squared plus blah plus 2, if you take a derivative, if you figure out the velocity, in other words, you just do power rule, right? Like the derivative of 5t squared, and I hope you understand what I'm talking about. Like you bring down the power, so you multiply the 2 by the 5 and you get 10, and the power goes down by 1, so you have 10t to the first. Like I'm doing a little bit fast, but I think you do know this from calculus, right? If you have x equals 5t squared plus 3t plus 2, the first derivative is 10t plus 3, right? Like plus 0. Then you take the derivative again, and you'll get 10 plus 0, right? So this is kind of like an x equals 1/2 at squared plus v naught t. You have something that's moving. It can have a velocity, but the velocity is also changing, so it has an acceleration. But if you take the derivative of that, you get 0. The derivative of a constant is always 0. So like there's something free falling in physics that has an acceleration of 9.8 meters per second squared. That's like a number that doesn't change. We say that something is free falling. You can describe its motion with 1/2 at squared, t to the second power. What we're really saying is there is a second derivative there. There is, and it's called gravity. It's called 9.8, but there's no third derivative or fourth derivative or fifth derivative. The derivatives stop after number 2. If you have a second degree polynomial. And technically, you know this already, I'm just reminding you, but maybe you've noticed it, maybe you've not. If you have a second degree polynomial, you can take 2 derivatives, and after that, all derivatives are 0. If we had a third degree polynomial, like x equals 5t cubed or something, we could take 3 derivatives. We could take a velocity, an acceleration, and a jerk, but then after that, the derivatives would stop, right? Like in other words, any finite degree polynomial, any algebraic equation has a finite number of derivatives. And then after that, all the rates of change are 0. So we can say that some kind of derivative is constant, like something free falling has a constant acceleration. It has a change in velocity, but it doesn't have a change in the change, right? That's like that situation. On the other hand, I'm just making up an example. So I'm intentionally making an example that's like the one we just did, but not exactly the same, just so you can see that it's a general principle. If you have something like x equals 5 to the 2t, right, which is like the answer we just got for sidebar 2. If you have that, okay, the derivative of that, I'm just going to do it. I mean, if anybody wants to throw this in, I'm happy to hear from you. But if I want to do the derivative of this now, I don't just do power rule, right? I have an e here. Well, I guess I do want to ask, like, what is, if you have the function, if you have x equals e to the t, what's the derivative of that? Does anybody want to say? Like, what is the derivative of e to the x? Does anybody want to say, just to make sure I'm not crazy or that I haven't lost everybody? If I say y equal, here, I'll write it.
It's just e to the x.
Yes, thank you. Phew. Yes, awesome. That's awesome. Yes, thank you both for being right about that and for paying attention. Yeah, so like what Caleb's saying is like the derivative of exponential functions are exponential functions themselves. If you're given e to the x in a math class, the derivative of that is e to the x. And same thing here. I happen to be talking about e to the t, but the derivative of it will be e to the t. However, there's also even, just to keep us realistic and honest, there's even a number in there. There's a constant next to the t, like there was in my other example, and there is here, and there will be in the future. So I'm going to add to what Caleb, I have to first of all note what Caleb just said, which is that the derivative of e to the blah is e to the blah. Plus now I also have to do a chain rule, right? I'm going to have to do, and someone was asking about this like last week. It might've been Caleb actually, or maybe it was Avery. Someone was asking about chain rule last week. Here, to cut to the chase, this derivative would be, right? Does everybody see that, right? Like I actually had to take the 2 out, so to speak. Maybe there's more steps that I should fill in, but right. And here's my point. If I took another derivative, it would happen again. And if I took another derivative, it would happen again. And what I'm really trying to say here is that one thing one aspect of exponential functions that is very different from polynomial functions, an aspect that could make them more intimidating or could also make them much more interesting, is note with exponential functions, the derivative of an exponential function is itself an exponential function. So the derivatives never stop, right? This is really important. The derivatives of exponential functions don't stop. We can say, and I can go back to that page in a minute.
Can you go back, Professor?
Yes, absolutely. Hold on one second. Yes, let me just write this before I forget. But yes, absolutely. Hold on.
Thank you.
And tell me when, if that's.
You can move on, Professor. Thank you.
All right, thank you. Awesome. Okay. So what I'm saying, and this is all of a sudden like we're in math land here, right? And believe me, I still know we are still in the middle of the last question of the first homework assignment. It's just that way. I mean, and this is what real physics is like. It's a simple physical question, but all of a sudden it's like, whoa, something is going on here. Well, you'll see in a minute. Anyway, I'm saying algebraic or power functions are finitely differentiable. You can take derivatives to a certain point and eventually, and you hit 0. And what point is that? Well, it depends on the power of the function. The lower the power of the function, the fewer derivatives you can take before you just bottom out on a constant or on 0. Whereas Okay. First thing I'm just trying to say here is that some functions, typical functions, algebraic functions, power functions, they have rates of change which are finite. Ultimately, you can get to a point where the rate of change is nothing. Like free falling objects, they change their position in time, so they have a velocity. They change their velocity, so they have an acceleration. But the acceleration is a constant. They don't actually have a jerk or a whip or snap or a crackle or a pop. I love that. Or anything like that. If we all get cut off, by the way, it's because my computer runs out of batteries, and that is actually, my plug broke. There's a distinct possibility that my computer is completely going to run out of batteries before this class is over. If that happens, give me 2 minutes to try to find a chord, and forgive me. But if this class just suddenly dies and I don't come back in 2 minutes, it's because there's literally nothing I can do. And I apologize in advance if that happens, and I'll see you tomorrow if that happens. So let me say again, I'm not actually joking. This is sort of pathetic, but if all of a sudden this class just ends, give me 2 minutes to try to find a chord, but I might not be able to. So if you don't see me in 2 minutes, then we're just done, and I apologize, and I will post all the notes in the video and all that if that happens in the next two. And yes, no,
Okay,
okay, thank you. And yes, if that happens, I will still post the recording of all this and everything. We'll end 20 minutes early. In fact, give me a second right now to see if I could, pardon me for 1 minute. Sorry. All right. Thank you. I did find a chord. So class will go to 3:55. And if you're really paying attention, you'll just notice that I teach in suit jackets and shorts, which there you go. That's the beauty of Zoom. It's like graduating in a cap and gown and your underwear. Sorry. And yes, the recording will, okay. So anyway, sorry, I found a chord and we will go to the end. And all right, what I'm trying to say right now is exponential functions are an example of a larger family of functions, ultimately known as transcendental functions. And those functions are a little bit more complicated than like x squared or x cubed or x to the fourth. They're more complicated because the rate of change of the function relates to the function itself. Okay, that sounds like very mathematically weird, but in fact, it's exactly the situation that we have at hand with the mass on a spring. Okay, in other words, what I want you to notice is if you have an E function, if something is moving in an exponential way, that means necessarily that it has a velocity, it has a derivative of velocity, but it also has an acceleration, but it also has a derivative of that, a jerk, and it also has a derivative of that, a snap. It like transcendental functions have rates of change which produce rates of change, which produce rates of change, which is, remember, the kind of situation that seems to be happening with the mass on the spring. Let me now finally go back to the mass on the spring. And I'm not saying, and I'm trying to explain stuff here. I am not saying that you were supposed to have done all of this, all these sidebars and stuff just to do question number 9. Of course not. You're just supposed to do whatever you can do to make question 9 work. And you'll ultimately see what the answer is to that soon. But I am showing you why even something that's phrased simply in physics may still entail a whole larger amount of not easy thought. It's also why you get to take as long as you want with homeworks and all that. Let me go back to question 9 now. And again, wherever you are on the homework, just tangent in and we'll just keep going. But in number 9, from homework 1, simple to phrase, but hard to, we had this, we had this is a differential equation because here the derivative is being related to x, not to t. Okay, this is illegible. I should put this on 2 pages. But what I'm saying here, summary of that whole sidebar in a way is alert, alert, alert. We have here that a derivative of x with respect to t is being related to x. It's not being related to t. It's being related to the dependent variable. So we have a situation here where the derivative is dependent on the function itself. Whatever the answer to this thing is, however x is related to t, it's not going to be x equals 1/2 at squared or something like that. It's not going to be a good old function from physics 1. It's not going to be, in other words, it's not going to be a power function because power functions don't relate to their own derivatives the way this thing does. Put another way, the answers, the solutions to differential equations are never power functions. They're always something exotic, like an exponential function or maybe something else. They're always some kind of transcendental function because they're always some kind of function that's building on itself, that is changing in a way that's related to itself. In other words, put one last final way, what we have here is an example of feedback. This is actually what's meant by feedback. Like you all know what feedback is in the most annoying auditory case. Like if you put a microphone near a speaker, right? The sound comes out of the speaker, but then goes into the microphone and then comes out of the speaker and then comes into the microphone and then comes out of the speaker. And so it feeds on itself. And what you end up, and you get this huge buildup of the sound because cause is being fed in, because cause is being fed in to the microphone and turns into effect, which is something that comes out of the speaker. But then that effect becomes a cause. It goes back into the microphone. So it feeds on itself and it feeds back. And you all know from various experiences, if you put a microphone too near a speaker, all of a sudden the sound builds on itself, the pitches build on itself. And when you go, like this really annoying, screeching, high-pitched, loud thing, right? That's exponential feedback, literally feedback. Anytime a function changes in a way that is built on itself, anytime that effect gets pumped into cause and back again, that's a differential equation or that's a transcendental function. How is that? Where is that in the spring? Remember the spring case here, what we have. And I'm trying to unpack this. I'm trying to explain to everybody both why this is interesting to me and exciting and why it ultimately applies all this higher math and higher things that we're going to do. I am not saying that you were supposed to know all this going into the problem, not at all. And again, please note, I know we're spending 3 days going over one homework sheet. It's not and you have many days to do it. I'm telling you that this is where physics is simple but not easy. I'm not expecting that you thought, and you don't need to have thought this all through in order to get all the points on the homework, not at all, right? But bear with me, please, and see, like, wow, simple question in the homework. What is x as a function of t? But whoa, when we stand back and look at it, something kind of funny is going on. What we're saying here in English is that in general, if you want to know where something is in physics, if you want to know where the mass on the spring is, in general in physics, what we say is, well, all you need to know is the acceleration. If you know the derivative, the second derivative, if you know the acceleration, then you can predict the position. But this statement here is saying, yeah, but the acceleration depends on position. So we're saying if you want to know the position, you need to know the acceleration. But if you want to know the acceleration, it depends on position. It's cause, effect, cause, effect, cause, effect feedback. This is a differential equation. The rate of change of the function depends on the function itself. Now, I want to unpack it. I want to get an answer. I know we only have 15 minutes today. I'm almost all this. I'm still only back to where I was on Wednesday. I want to unpack this. You might say, so my first lesson is we can't just integrate both sides. That's what I was trying to show in sidebar 1. We cannot just integrate. We have to be more careful than that. We could use the method of sidebar 2, except that here those were sidebars because they were comparatively simple examples meant to illustrate a larger point. But here we actually have a more complicated point. Here it's the second derivative of x with respect to t that is being related to x. Now, if this were just a math curriculum, if this were a math class, we would spend a month on looking at first derivatives, and then we would proceed in the next step to doing second derivatives. We wouldn't start the whole class with a second derivative. But this is physics. We're just looking at a seemingly simple physics situation of just something going back and forth and back and forth. And when we analyze it with our physical laws, we see, oh gosh, it appears that some second derivative is being related to the function. In other words, the first differential equation we ever slam our heads into in physics is a second order differential equation, just because that's what nature puts in our face. Like, and that's how Hooke and Newton had to figure it out. If you see what I'm saying, like, and that's why differential equations are not required for this class. I mean, we're doing this together now because that's what the physics demands. But we're proceeding in the order of physics simplicity to physics complexity, not like the alphabet of math. In other words, this is a second order differential equation. Okay, and we just have a second order differential equation because we just have a second derivative there. And the reason we have a second derivative there is because f equals ma. It's just like the way it is, right? So I hope I didn't just lose. Okay, so sidebar 1 was meant to be an example of an equation that has a derivative in it. Sidebar 2 is an example of a differential equation and an example of how differential equation, well, actually, let me write this down. I'm sorry.
Professor?
Oh, yeah, sorry.
Just to kind of summarize for myself.
Yeah.
So like dealing with differential equations is kind of like implicit integration, right?
It's very much like implicit integration. That's a good analogy. Yes, like implicit integration in 2 ways. That's good. Number 1, because it's implicit, yes. And number 2, it's also like, that's a really good example. And obviously some people in the room might know more what you're saying than others, but yes, that's a good analogy. Also because like with implicit integration, you don't always know in advance whether it's going to work or not. And you don't always know in advance if there is an actual answer, or I guess it's the same thing. And you don't always know in advance when to use implicit integration. Like, you sort of have to just learn from experience when it's going to be a good technique and when it's not. And in all of those ways, yes, a differential, a differential equation is very much like that. That in order to solve it, we just have to come up with different techniques that work over experience, and sometimes they don't work at all. But yes, right, it is more like implicit integration than just like any old integration. Absolutely, that's good.
Got it.
Cool. So what was I just going to say? Oh yeah, okay. So okay, and honestly, actually, to every, all right, let me write this down. But that's also good enough to everybody. The other reason I have to spend so much time on this, like I'm going to give you we're going to get the solution to this differential equation. And like many of you have already seen, the solution's all over the web. And I mean, I know that. I mean, and it's also why it's possible to do this homework just in one night or whatever. We're going to get a solution that you can just look up on the web or in a book, and the solution's right. And we can show that it's right. But I'm spending a long time on this to show everybody, because I don't believe in just pulling things out of a hat. And I want everybody to know, I want everybody to know that with differentiation, with derivatives, once you learn them, then there's procedures, and if you're presented with a problem, you have to differentiate. You just do the procedure and you know it's going to work, and it gets you an answer. It's like an algorithm. You actually can memorize procedures for differentiation and rely on them. With integration and differential equations, it is more puzzle solving. There is not you cannot guarantee that any one technique will necessarily work for any one type of problem. I mean, so this is just feeding off that answer again. And so what we have to do here, especially for this type of problem, is we have to make educated guesses and then verify them. There is no other way. It is puzzle solving because it is that sophisticated of a situation. I guess just trying to say to everybody. So just to summarize, and I'm glad, I totally appreciate that you guys are like trying to stop and summarize as we go. That's really important. And here's my summary of the same thing. Well, all right. So I'm just going to read this out loud before I'm going to go to the next page in a moment. But so in sum thus far, sidebar 1 showed an equation with a derivative in it, and it solved for the original function. Like in sidebar 1, we had like a dx over dt equals blah times t. We solved for x as a function of t. We got kind of a standard power function as a result. Sidebar 2 did show a differential equation just by like switching t for x. We suddenly had something that depended on itself, in effect, and we solved that by using one particular technique, and we got an original function. We got an exponential function. So sidebar 1 was just like equation that had a derivative in it. Sidebar 2 was an actual differential equation, but it was first order differential equation. We were given an equation that was revolving around a first derivative. And that already led us to an exponential solution. Like hopefully it wasn't crazy. Hopefully everybody followed it, but it was our first differential equation. It led to a feedback kind of solution. Now back to homework 1 then, or thing on the spring. Oh yeah, yeah. I hope that doesn't. Oh my God, what just happened? Oh my God. I hope. Okay. Sorry. All right. So now finally back to physics. And again, the physics, we have the seemingly simple situation, just a mass going back and forth on a spring. But evidently it presents to us a second order differential equation. And we have to solve. We're going to solve for the same thing we've been solving for in every sidebar. We're solving for x as a function of t. But I backed, and I know I only have 7 minutes, and it is what it is. But I backed up on those two sidebars just to show how much math is behind this situation. It's a simple physics situation, but it's suddenly inviting. I don't mean it's neat. I mean, it's a fundamental physics situation, a place to start, just a mass on us, but it seems to all of a sudden be forcing us to deal with a second order differential equation. Now that I've shown you what is going on with a first order differential equation, like in sidebar 2, I'm trying to show you the significance or the properties of it. But I want to say we used one technique that worked in sidebar number 2. I was able to just multiply. Technically, what I did was called separating it. I separated the differentials, put them on both sides and then integrated. That is not going to work here because this is a second derivative and I can't just like separate them like that. So what I do here finally to go back, I know I only have 6 minutes, but to go back, so I have to use a different technique. The new technique here is technically is guess and check, conjecture and verify. However, the conjecture that we're going to use everything at our power to conjecture. We're going to say to ourselves, we need a function. Okay, I know that even with only 5 minutes left, I'm just now up to where I was at the end of last Wednesday. I'm aware of that. Hopefully this is clarifying things for some people. Again, if it's going too slow, I apologize. It will go faster. But I'm saying now, I'm going to guess a function and I'm going to be able to verify it. Guessing is not sound mathematical or scientific, but it actually is. It's totally mathematically and scientifically rigorous to guess as long as you have a means of verifying your guess. We will have a means. We are looking for a function which, when you differentiate it twice, you get back the original function times a constant times a negative sign, right? Like we have d2x equals negative k over mx. We're looking for something that when you take its derivative and then you take its derivative again, you get back to itself, like x, right? So like so from math, we're looking for some kind of function like that. Like maybe e to the x would be one example. You take the derivative of e to the x, you get e to the x again. You take the derivative of it again, like a second time, you still have e to the x. That sounds like a pretty good candidate. Like e to the x could be a good type of answer here if I'm just thinking in terms of math. But if I'm also thinking in terms of physics and the physical situation of something going back and forth and back and forth and back and forth, and if I think of my lab data, I think of something going back and forth along the position axis as time progresses, then I wouldn't think of an exponential function or an exponential function. I would think of more like a sine or cosine function, right? If I were thinking about the physical data. And hey, sines and cosines are like exponentials in that the derivative of cosine is negative sine. The derivative of negative sine is negative cosine. Cosine, if you take two derivatives, does spit back cosine only with a negative sign. And that negative sign is good, actually, because our differential equation says, I didn't make it dark enough, but our differential equation here says we want something that when you differentiate it twice, you get back itself times some constants times a negative sign. So cosine is a really good guess. I know only have 2 minutes. I know I'm just about up to where I was Wednesday, but I'm saying cosine, I'm guessing because it has the mathematical and physical properties that seem reasonable. It's just a guess. It doesn't prove that it's right, but it's a guess. Now I want to go one step further since I've spent all this time with 2 minutes. Notice every time I'm writing cosine here, I'm putting dashes like before it and between the t. That's because of units, because I'm a physicist, not a mathematician. Okay, this is my last page. I know there's a minute and a half. This is the last page. I promise I'm watching. We have 1 minute. Okay. And we'll just pick up here where we are. Again, just do whatever you're up to in the homework, and so will I. And we'll pick up here here tomorrow. But why do I keep putting in blank spots into my guess? Why guess? Oh yeah, because the blank spots are one for arbitrary, and this is where we're going to stop right now, but for arbitrary constants, all that work I did today, yeah, oh yes, this is totally going to help with, yes, this should help with homework too. Good question, it should, it really should. And if it doesn't, we'll get to it, but yes, it should. The blank spots are about arbitrary constants. Remember all that, every time we did an integral in sidebar 1 and sidebar 2, we were doing an indefinite integral, and all of a sudden arbitrary constants popped up because they're indefinite integrals. So I'm leaving room for those. That's reason number 1. And reason number 2 is we are physicists. We have to look at units, which is where I'm going to end right now. I'm just going to say this. I'm guessing cosine, but I'm not just guessing x equals the cosine of t, because as a physicist, I cannot take the cosine of a second. Time is measured in seconds or minutes or hours or whatever. And you can't take the cosine of time. You have to take the cosine of an angle. So I'm going to have to, if cosine is right at all, I'm going to have to multiply those seconds by some kind of constant that adjusts the units and turns them into radians. I'm going to have to multiply by something measured in radians per second so that I can take the cosine. Then that whole thing, I'm going to have to multiply by some kind of constant that's measured in meters so that my whole answer gives me an x measured in meters. That's why the blank spots. So I'm going to have to figure out what goes in the blank spots, but I'm not going to do that now. I'm sorry that this has taken so long. Again, it will, hopefully you've learned something. It will build as it goes. Just do whatever is next in the homework. If you still can't do homework 2, you're not going to be punished. We're still not up to it, but I think this will help with homework 2. Okay, I'm done. I'm just going to stand here and wait in case there are any quick questions or anything, but you guys are good to go. Thank you. Yes, thank you very much. See you tomorrow.
Thank you, Professor. Have a great day and see you tomorrow.
Yes, see you tomorrow. Awesome. You too have a
Thank you very much.
Thank you, guys.
Were these the methods that we were supposed to use in homework 2?
No, you're supposed to use whatever you used. I mean, these are thought process. What this is, no, I mean, I'm saying a lot here. I am saying that some of the things I'm saying that you're supposed to think in a linear fashion about, oh, I'm sorry, wait, in homework 2 or homework 1? In which
Homework
one?
2.
Oh, in 2. Well, yeah, actually, if you got the answers right in homework 2 without doing any of this, then you're and you did things honestly, then you're probably fine. But what these really are, in a way, are a lot of observations that I think you'll notice as you're doing homework 2, or would have noticed in your own words, or will notice. Like I'm not asking you to have thought through all of this to do homework 2, but I'm kind of saying I think that that if you look at what you're doing in homework 2, especially those early exercises, like even if you didn't think all these words, hopefully this is pointing out things that become observable in homework 2, such as when you do when you're doing equations that have t on the right side, you get power function answers, and when you get like exponential answers. But no, so these are more observations that hopefully will be reinforced by homework 2 and vice versa. But I'm not asking you to have thought through all of this in order. Yeah. Okay. Sorry. Yeah.
Okay. Yeah. Well, because like some of the questions where it's like the second derivative or whatever is equal to, I thought it was like explicitly asking like take the second derivative and then equate it to that, not necessarily that this is a differential equation that you have to solve.
Right, right. No, you're right. I think, I mean, if I'm remembering the questions correctly, that you're right. I mean, another way to look at it, no, you're right. And I'm not disagreeing. Partly what I'm sort of trying to do, kind of always in physics and math, is I'm trying to show that a lot of times you're doing differential equations without knowing it. And I'm trying to show where people figured out how to do differential equations when they originally didn't know it. I'm sort of just trying to define all the vocabulary in a long, elaborate way so that the vocabulary in the end doesn't get in the way. But if that makes any sense. But yes, you're totally right. You didn't have to, you were supposed to just do those exercises whether or not you knew the word differential equation, if that makes sense.
Good.
Okay. All right. Cool.
Thank you.
Good point. Good point. All right. All right. Anybody else cool or other questions? Or again, you guys can totally go. I'm just standing here in case there was other questions. But if you don't have questions, you guys can go and I can see. Oh, let me look in the chat. But if everybody's good, oh, okay. But I'm good if you guys are good. Whoever, like Noelia, you're good. Edie, you're good. Oh, thank you. All right, cool. Thank you, Edie.
Professor.
Oh, yes. Hi.
Um, uh, I just wanted to ask, what is because I'm trying to like study it like later, because what is this like topic that we did today like called like in general?
Oh,
So,
yeah.
because I'm not gonna, because it was kind of, because I kind of want to like study like the topic that we did today, like
What
like
we're
later.
Yeah, good question. It's harmonic oscillation. I haven't actually used the word yet, but yeah, it's harmonic oscillation that we're studying.
Oh, okay. Okay, I was wondering because I'm not gonna lie, it was kind of confusing at some points in the class. That's why I just wanted to ask so I can try to like understand it like later.
No, fair enough. And I know, yeah, it's harmonic oscillation, and hopefully it'll start getting even more clear tomorrow when I relate it back to the. But yes, it's I'm sort of trying to do all the background math that we need that I think people are usually kind of fuzzy on when they get here. So it seems even fuzzier now because it's not clear why I'm talking about all this stuff, but it's kind of the underlying math for the physics topic of harmonic oscillation. So yeah, that's a very fair question. Also, can I ask you, as long as you're here, you have not heard back from Professor Wu yet, right?
He actually I think emailed me like at like 1:30 in the morning, but I didn't find out till like I woke up this morning.
Oh,
So
okay.
but I messaged him back because I wasn't able to go to lab today because my laptop was acting up. But he told me in the email saying that just like come to class and we'll figure it out.
Oh, okay.
We'll figure it out. Just like I guess after like the when I come back like for the lab, just like after class and just stay and then we'll talk and I'll figure everything out. He said.
Great. Okay. No, that's good. I'm glad that's working out. And yeah, and I forget, can you just remind me, do you have lab right now, right after this, or you have lab before class?
Oh, I looked up what time I have. I think it starts at like 10:15. It's before lecture.
It's before lecture.
I think it's like 10:15 to like 12 something.
Well,
But yeah, it starts before lab.
Okay, it's before. Okay. So yeah, so I'm glad he got back to you. So yeah, I'm sure I know this all goes fast, but it'll even out. You'll get caught up. It'll get caught up and work out, I'm sure.
Thank you. Do we have like a homework 3? Like
it is a homework 3 and it is in the Google Classroom, but honestly, I wouldn't even worry about it yet because I'm not. Just try to do homework 2, and no one's going to be marked late or anything like that. But I definitely would never mark you late for homeworks that I haven't even gotten up to yet anyway. So there is a homework 3, but I would right now just worry about homework 2 because I haven't even gotten up to going over it yet.
Okay, thank you.
Cool. All right, no problem. Okay.
Thank you, sir. Have a good day.
You too. Cool. And Caleb or Noelia or Janine, you guys good or question? Because I'm good if you're good. You guys are good? Going once, going twice. All right, so I'm going to say goodbye if Noelia and Janine and Caleb, if you guys are good, I'm good. Okay, I'm gonna go. Okay, going once, going twice. Okay, bye guys.